on behalf of Team Elementary. Today with us we have Professor Santanu Mukherjee, who was kind enough to take time from his busy schedule and accept our invitation. In this lecture series, we will be hearing from eminent chemists who are actively involved in research with the idea of introducing and learning about new and upcoming fields in chemistry. I hope you all enjoy the talk. Professor Santanu Mukherjee is an associate professor in the Department of Organic Chemistry at the Indian Institute of Science, Bengaluru. His research interest is focused on asymmetric catalysis with an emphasis on the discovery of new enantioselective transformation and recently iridium catalyzed asymmetric allylic substitution reaction. He received his BSc in 2000 from RK Mission Residential College, Narendra, Narendrapur, India, and then obtained his MSc from the Indian Institute of Technology, Kanpur in 2002 under the guidance of Professor Parimal K. Bharadwaj. He joined Professor Albrecht Bersickel's lab at the University of Cologne, Germany for his doctorate, and he was a postdoctoral fellow with Professor Benjamin List at Max Planck Institute for Kohlenforschung in Mülheim an der Ruhr, Germany till 2008, post which he was a postdoctoral fellow with Professor E. J. Corey at Harvard University. He is a fellow of the Royal Society of Chemistry, London. He has been awarded the Chemical Research Society of India Bronze Medal in 2019 and the A.V. Rama Rao Young Scientist Award for the year 2019. He was a member of the editorial advisory board of the Journal of Organic Chemistry and is currently the associate editor of the Organic and Biomolecular Chemistry. Today, Professor Santanu Mukherjee will be discussing with us the basics of organic stereochemistry in the backdrop of asymmetric synthesis. He will also be talking about a few case studies on the use of catalysis in controlling stereochemical outcomes of a reaction as well as its applications. He will be taking questions from the audience post the talk. I request the audience to use the Q&A box to ask questions, and the questions will be read out by the moderators. Without further ado, I request Professor Santanu to address the audience.
Thank you, Nikita, for a very kind introduction, and I would like to thank Avinav and all of you, your team, for arranging this lecture series, elementary lecture series, at this very difficult time that we are going through. Of course, all of you are at home, and I think in some form or another, we are all affected by this COVID-19 pandemic that we are currently going through. Hopefully, this should soon pass. So within this lockdown and so on, so we are trying to do our best in terms of teaching and research, and it's a great effort from all of you to arrange this type of lecture series to keep yourself and also us engaged along with you, and it's great to interact with you all the time. So today I'll talk a little bit about organic stereochemistry and how why it is important and its implications in real life, and how the challenges of getting an energy of pure compounds are solved using catalysis. And towards the very end of the talk, I will give a couple of examples from our lab just to give you an idea. Of course, as many of you are fresh from high school and some of you are in your first or second year of your BSc, I wouldn't expect you to know a lot about the intricacies of research, but so I will start from a very basic. At the beginning, it may appear a little bit boring. Please bear with me. I'm sure towards the end, when I finish the talk, you will learn quite a bit of things that you have not been exposed to yet. Now, organic stereochemistry is nothing but studying of three-dimensional molecules. Now, as you know, that we are all surrounded by three-dimensional objects. Like whenever you look around, we are surrounded by three-dimensional objects, which we need to, at times, we need to represent them in two dimensions. Like for example, the tree, you can draw it in this fashion, including ourselves, like our machineries of our body. So as you know, that proteins and DNAs are two of the most important machineries of our body, and almost all the functions of our body are regulated by these two machineries. And then if you look at them carefully, they are fundamental building blocks of this. And of course, the protein and DNA or the nucleic acid themselves, they are actually three-dimensional molecules. For example, proteins are composed of amino acids, and nucleotides or DNA, they are composed of sugars. And not just that, you can see here, I have indicated L and D here. So basically, whenever you're looking at an amino acid or sugar, both of them are three-dimensional molecules and they can have multiple isomers. So L and D basically represent one of the possible isomers. In case of an amino acid, it's one of the two possible isomers. In case of sugar also, there are many isomers possible. It's just one of them it represents. So therefore, in that sense, we can be called as homochiral. So this is again a technical term I'm using a bit too early. So homochiral basically means we are composed of only single isomer of many different possibilities. However, there are two-dimensional materials as well, objects like starting from the benzene ring. If you think of, you just stitch them together, you come to graphene. And I'm sure all of you are familiar with what graphene is. And it's basically the term came from graphite and the suffix "in", that is unsaturation. And it is considered to be, it is an one atom thick. So that means it's a two-dimensional material and it's very thin. So just to give you an idea how thin a graphene sheet is, it's about 3 million graphene sheets. If you put together, they will constitute 1 millimeter thickness of a 1 millimeter thickness. So, and this is of course coming from graphite, right? And for their research in graphenes and the discovery and isolation or preparation of that, Andre Geim and Oshilov were given the Physics Nobel Prize in 2010. But anyway, our discussion today will not be two-dimensional objects, but will be three-dimensional organic molecules. So, which basically means that arrangements of atoms in space. And now, why it is important or how it comes to the point that we need to worry about arrangements of atoms in space, we need to look at the aspects of isomers. So what do you mean by isomers and isomerism? So we'll start with the very basic aspects of that is isomerism. So we all are familiar, I'm sure all of you know the definition of isomerism. It's basically the identical molecular formula but different arrangement of their atoms. Now, how the arrangements of their atoms or how the atoms are arranged, depending on that, isomerism can be of two different types. One is the structural isomer, other one is the stereochemical isomer. So we'll be discussing about stereochemical isomers and various properties and their synthesis. But before that, let's have a brief look about the structural isomers. Now, these are also called constitutional isomers. So in this case, again, the molecular formula is same, like always, and but their connectivity of the atoms are different. And based on that, there are three different types of structural isomers known. One is called chain isomers, which is, for example, if you take a butane, you can have N-butane and isobutane. These are the two different chain isomers. Their connectivities are different. There can be position of a particular functional group can be different. For example, if you look at 1-propanol and 2-propanol, this is also known as isopropanol. So this is also, these are basically the functional group is changing from one position to another. Otherwise, the molecular formula is the same. Therefore, the connectivity of the oxygen was moving from 1 to 2 position here. You can also have difference in functional group themselves, like this molecular formula C2H6O can have two different functional group. One is alcohol, other one is ether in the form of methoxymethane or dimethyl ether and ethanol. Now, I'm writing these formulas here in a very naive fashion, so where you can see all the hydrogen and carbon and oxygen and everything, but sometimes they're difficult to follow. And if you have a cartoon representation of this type, you will be able to follow them much easier. So it's almost like representing something in a very quick manner or looking at a molecule from a different perspective. Like this is, all of us are familiar with this painting, it's Mona Lisa. Now you can look at the painting from the edge, it will look like this. Now if you represent this painting like this from the edge, it won't show anything. So therefore a correct representation is also important. So you can represent something like this. It's of course a very rough drawing, but you can look at this and tell, yes, this is Mona Lisa. Similarly, if you look at an organic molecule that is called linoleic acid, and if I ask you immediately to find the functional group present in this, you may need a few seconds to locate that. On the other hand, if I simply remove the H and C from this molecule and represent it this type of long chain representation, you don't need any time. Simply by looking at it, you can tell that there are two olefins and one carboxylic acid present. So therefore, representing the molecules in the most convenient and correct form is also very important. So now on, whatever the structures we will look at, we'll be representing in this fashion and not in this fashion now. Now, again, coming back to the isomerism, so we already talked about structural isomerism. Let's come to the stereoisomers. Now, in case of the stereoisomers, not only the molecular formulas are identical, but also the connectivity of atoms are also identical. So what is different is that their arrangement in three-dimensional space. And then stereoisomers can also be of two different types. One is called configurational isomer, like you can see cis and trans E2-butene. So what is the configurational isomer? So these are basically not interchangeable without breaking a bond. So if you want to interconvert one configurational isomer to another one, you can see the atom connectivities are very similar in both the cases or same. It is just the arrangement of them in space are different because these are two methyls are trans, these two are cis. So therefore, it is not a spontaneous process to interconvert the configurational isomers. So therefore, they are stable and they can be isolable at room temperature. On the other hand, you have something called conformational isomers, where a molecule gives rise to various isomers simply by rotation of a single bond. So this is, I did not represent in a three-dimensional manner. I just put it here. You can see if you rotate across this CC bond, you can get various conformation. I also did not tell that if you rotate across this CC bond or CH bond, you can also get various other conformation as well. So therefore, there can be numerous conformational isomers, and their energy level or energy required for their interconversion is actually very less. Therefore, they're spontaneous process. As a result, you will not be able to isolate them in most cases unless this interconversion or the bond rotation is hindered, and in those cases, even the conformational isomers can give rise to isolable conformational isomers. So we'll not come to that today. And these are also, of course, called rotational isomers or rotamers as well. Now, if you look at the configurational isomers, there are again two different types. One is the enantiomers. Just give a couple of examples here, which are basically nothing but mirror image relationship, not superimposable mirror image, like almost like our two hands. And these are, of course, they have identical properties in almost everything except the optical rotation. We'll come to that in another few minutes. But there are also pair of stereoisomers, or there are multiple stereoisomers possible. They are still isomers, but they are not mirror images at all. For example, if you look at these two compounds, you can see they are not mirror image clearly, although the molecular formula and the atom connectivity are same. They are, of course, different in terms of their spatial arrangements. So therefore, these two are called diastereoisomers. And again, this compound can have, so typically when a molecule have one chiral center, you can have only a pair of enantiomers, or generally enantiomer appears in pairs. On the other hand, diastereomers can be any number as well. For example, these two are enantiomers, and again, these two are diastereomers. So therefore, these two are diastereomers, these two are also diastereomers. And again, if you look at more complicated molecule of this type, which is not symmetrical, this was a symmetrical, this is not symmetrical. Here you have two pairs of enantiomers and then two pairs of diastereoisomers. Now, how do you know the number of stereoisomers in a molecule? So that depends on how many stereocenter or the chiral center is present in a molecule. Typically, the formula is 2 to the power n, but not always. You have to take some care. Like typically, if it is a one chiral center, you can have two stereoisomers. That is fixed, and they are enantiomers, of course. Now, if the number of stereoisomer goes beyond 1, then you can have the number 2 to the power n, that is 2 to the power 2, that is 4. That's the maximum number of stereoisomers possible, and that depends on whether the two chiral centers are identical or not. Like in this case, they are not identical, two chiral centers are different. Therefore, you have two pairs of diastereomers, and each diastereomer have a pair of enantiomers. But if the chiral centers are identical, then the formula changes a little bit. I will not go into the details. I'm sure you have already studied them in the class, or you'll be looking at them. So here actually you can divide the molecule into two halves. So therefore these are identical. Now in this case you can have, so these are identical, but these two are enantiomers. So total number of stereoisomers are basically 3. So let's just summarize it. Isomerism. If you have the same molecular formula, if the structure is identical, then they are called homomers. If they are not, they are called isomers. Now if you have same bonding connectivity or the atom connectivity, or if they are not, they are called constitutional isomers, and there are chain, position, and functional group isomers. But if they are same atom connectivity, then they are called stereoisomers, and they can be of different type. If it is mirror image is non-superimposable, or they are of mirror image relationship, they are called enantiomers. And if their mirror image is or they are not of mirror image relationship, they are called diastereoisomers. And now, as I was mentioning, that enantiomers will have the same physical properties, that is melting point, boiling point, solubility, and so on. The only difference is in the direction of optical rotation. So now why is that? We'll come to that again in a minute. Whereas the diastereoisomers are very different compounds, so everything can be different. So one can be liquid, other can be solid, and so on. They can be completely different, so there is no correlation between them. Now let's come back to the why there is a optical rotation is different for the different enantiomers. So now you know what is optical rotation. It is basically a rotation of a plane polarized light in the presence of a molecule, and that is measured by a polarimeter. So you have a light source, which is basically an electromagnetic radiation, and there are many vectors of that, and you use a polarizer to actually get only one vector, and that when passed through the sample solution or a liquid sample, it can actually rotate the plane of the plane polarized light, and then you analyze it, and you can see from this side. So if the plane is rotated to the right side or to the clockwise direction, you call it a plus sign, and if it goes to the opposite direction, it's called the minus sign, counterclockwise. So this is called if it is a clockwise, it is called dextrorotatory or a small d. You have seen D and L in case of an amino acid and sugar, but in those cases we are using capital D and capital L. So they are not the same as D and L here. Those are actually different nomenclature. So please do not mix up with dextrorotatory or levorotatory. Now, so what you see, what is this optical rotation depends upon? It depends upon, of course, the wavelength of the light and also the concentration of the solution. That means how many molecules that light is interacting with, if the molecule is chiral, of course. And of course, the path length of this tube, because depending on how short or how long the sample solution is or the sample cell is, the number of molecules will obviously be different. So therefore, this will change. Now, what is measured actually, or what you record, is something called specific rotation. So which is dependent only on the wavelength and the temperature. It does not depend on the path length of the cell or the concentration of the solution, because that is already taken into this consideration. Now, you typically, so the best way to find out whether a molecular compound is chiral or not is to check the optical rotation, but it comes with some set of guidelines, of course, because if you have an enantiomers, two of them are present in 1:1 ratio, you will not get any optical rotation. Again, we will come back to that at a later stage. So let's go to see what is chirality. As I mentioned, that when you have a molecule with a chiral center, it can exist as a two pair of enantiomers. That means two mirror image relationships, like our hand, as I've shown here. So they are called enantiomers. And now these enantiomers can have very different properties. Like I mentioned, of course, the first thing is that non-superimposable mirror image, but you will see that, as I said, there are only optical rotation is different, but other physical properties are same. So, but then you will see some compounds like limonene, for example, you can see I've given a plus and minus, that is like clockwise or counterclockwise rotation, and then R and S, that's the nomenclature. So one of them smells like orange, other smells like lemon. So R smells like orange and S smells like lemon. So why is that? Because why the smell is different. Similarly, if you look at carbon, one smells like spearmint, other smells like caraway seed. Now, we are smelling it, right? So are we symmetrical? So as I mentioned at the very beginning that our body consists of L amino acid and D sugars. So we are actually homochiral. We are chiral and homochiral. So therefore, these chiral molecules, when they come in contact with another chiral molecule, they start behaving differently. It is very similar to what you see on the nature, like many times you see the snails, and you will see there are most of the snails will have this spiral in only one direction. It is right-handed or left-handed helix if you consider them as a helix. And this almost like, and this recognition of a chiral molecule or the behavior of a chiral molecule in the presence of another chiral molecule, it is almost like wearing a gloves. If you put your hand to a left-hand gloves, right hand to a left-hand gloves, it feels different. Even if you are wearing the gloves in dark or your eyes are closed, you can feel whether you are putting the hand to the right gloves or shaking your hand. So this is another example where you do not need to see that. Just by holding somebody's hand, you know whether you are holding their right hand, if you are stretching your right hand or left hand. So this is basically the recognition of the two chiral molecules. They behave differently in presence of each other. So as a result, you can say that enantiomers are actually identical until they are placed in a chiral environment. So as you know, our body is chiral. So when you are smelling something, that means our olfactory senses are actually smelling it. So there it is chiral. So therefore, they recognize the two enantiomers differently. Now, what can be the consequence of that? Of course, smell is a prominent thing that you can figure out from that which compound is this, but it is not of a serious concern, right? Because if you are asking for an orange flavored compound or orange flavored toffee or an ice cream, you get a lemon flavored one. It's not a big deal. But when it comes to medicines or something that related to health related issues, it can be something significant. For example, you may be familiar with the medicine called L-Dopa. This is basically a medicine for Parkinson's disease. It's a neurotransmitter, whereas the D-Dopa, that is the enantiomer of that, is actually toxic. Even more disastrous example was probably the most infamous example was this drug called thalidomide. It was used as a painkiller in 1950s and 60s. Initially, it came as a painkiller, and like modern days aspirin, we keep seeing that there are many properties of aspirin, or many functions of aspirin. So there, here also people found that these thalidomides can have different function. For example, in addition to being painkiller, it can also act against nausea, particularly for pregnant women. So this was used as a drug against morning sickness of the pregnant women. So what was found actually, and they found it quite effective. So that was very popular among the pregnant women in 1950s. What they found out, by the way, this drug that time was administered as a racemic mixture, that is 1:1 mixture of the two enantiomers. And later on, it was found out that R enantiomer is an effective sedative agent, whereas the S enantiomer is teratogen. That means it's toxic and it led to severe birth defect. And there are probably some 20 or 25,000 patients or this type of so-called thalidomide babies were born in 1950s and 60s. So therefore, this drug was withdrawn. But in this case, we have to take the example with a bit of a caution, because you can see this is the chiral center and that is present alpha to a carbonyl. So therefore, you can imagine it can actually analyze in the presence of an acid or a base, particularly when there is a heteroatom present that makes it even more acidic because of the electron negative nature of the atom here, or electronegative atom. So therefore, even if a single enantiomer was introduced instead of a racemic, it would have had the same effect because it would have racemized in the body system. So now from these two examples, you can clearly see that it is important to have a single enantiomer of the molecule. Now, it is not always the medicines, but also agrochemical compounds can also have a lot of significance on that. So this is one of my favorite examples. So this is a compound that is it's called Japanese beetle pheromone, and there is a beetle in Japan, and the beetle and the larva, they destroy the crop, and there's a huge loss of crop that happens over the throughout the year. So what they realize that if you use this pheromone, it actually attracts a lots of these beetles and you can kill them. So they use this type of a bait or a trap where they use this molecule in a part of a solution and thousands of beetles get attracted. But it depends on not only the stereochemistry at the chiral center, but also on the double bond that is present in the molecule. So Z and R are the right combination in this case, and only 25 microgram of this molecule can actually catch thousands of beetles. Whereas the corresponding E isomer of these, even if it is R, that is virtually useless. Now, if you consider the corresponding enantiomer of this pheromone or this compound, that is not only inactive, it is actually a powerful inhibitor of the R enantiomer. Even if 1% of the S enantiomer actually kills the activity completely. So therefore, it is important to obtain a single enantiomer in pure form. Now we come to our discussion today. How do we access a single enantiomer? So this process is called asymmetric synthesis. So let me just tell you a brief idea about what asymmetric synthesis means before we go into taking some of the examples. So if you consider a simple reaction, that is addition of a nucleophile to a ketone, which is a prochiral ketone, that is an unsymmetrical ketone, and you know the two phases of the ketones are so-called pro-stereogenic phases. That means Re phase and C phase as we described them. And here if you add a nucleophile either from the bottom phase or the top phase, you get two different enantiomers. Now these two are the corresponding transition states. How do they look like? And you can see in this case the nucleophile is coming from the left side and this is from the right side. And if you look at the transition state, they are actually nothing but mirror image. So therefore they are enantiomeric. And as we have already seen that enantiomers have very similar properties. So therefore they actually their energy levels are identical. So therefore, if you look at the activation energy of this reaction, they will be identical in both directions. So therefore, you will get an equal amount of both the products if you react with the nucleophile. So this is an example here to do dimethyl cyclohexanone. If you add phenyl lithium, you get a 50-50 mixture of two enantiomers. On the other hand, if you add a nucleophile to a ketone in a chiral environment. Now assume that one of these two groups, R1 and R2, they are actually chiral. So therefore, the two transition states will no longer be enantiomeric, they will actually be diastereomeric. So therefore, you will get the products in unequal amount. So this is an example here. Instead of a 2,2-dimethyl cyclohexanone, I'm having a methyl group here. So therefore, this is a chiral center. So you can imagine one of these two, as I was telling, is chiral. So imagine this is R2 and this is R1. So therefore, whether the phenyl is coming from the bottom phase or from the top phase, that will give rise to two different diastereomers. And as I said, diastereomers are very different compounds. So their energy level will also be different. So therefore, one of them will give you, one of the products will be forming predominantly over the others. Now, so therefore, what you need to do eventually is to break the symmetry. And how do you do that? By introducing a chirality in the transition state. Now, how do you do that? There are many ways of doing that. So we have to basically break the symmetry and have these two different diastereomeric transition states. So there are various approaches. You can use chiral substrate as the previous example I have given. I will come with more examples. There is something called chiral auxiliary, chiral reagents, and chiral catalyst. So basically they are more or less in the similar order. And I will give you some of the examples of each category. And you can also see why, what are the advantages of having each of them and what are the limitations of each of them as well. So let's start with a chiral substrate. So what is called something called substrate-directed stereo control. So again, this is a very similar example like I have taken previously. In this case, you have an alpha chiral ketone, a methyl group at the 2 position here, and you are adding a alpha position, not a 2 position. You are adding a lithium aluminum hydride. Again, the hydride can come from the top face or from the bottom face. You can see if it is coming from the top face, you are getting a slight excess of that is 3:1 ratio. Now, a similar aldehyde, if you add a Grignard, again you are getting these two different, very same compound, but the ratios are different because in this case, the ethyl group is adding from the top face, that is here. Sorry, that is this one will give you the major product, another one is the minor product. So, and you have already studied probably, or you are studying them, it is dictated by something called Cramp's model. So this is another way of representing three-dimensional molecules. So I will not go into the details. And in this case, so you can basically, you are looking across this CC bond here. This is the ketone carbonyl, and this R is ethyl in this case. And then the three groups that are present here, phenyl, methyl, and H hydrogen, you can put them as a large, medium, and small. And the nucleophile will approach from the side of the, between the small side, not on the medium and large, not between the small and large, not between the medium and large. So that is called Cramp's model. It was by Donald Cramp. He proposed this model, and this can actually, from this, you can actually predict the stereochemistry, stereochemical outcome of this reaction. So, and so these are basically steric control. As I said, this is large and medium and so on. In some cases, you can also control through coordination. For example, you have this cyclohexenol. This is a single enantiomer. And if you do the epoxidation using perbenzoic acid, there are two possible isomers. As you can see, they are diastereoisomers. They are possible, and you can get the epoxide from the same phase as the existing OH group. And this is the way it is happening is by this solver transition state, where the OH forms an hydrogen bonding with peracid or perbenzoic acid. So therefore, the perbenzoic acid will approach from the same phase as the OH. As a result, you get this compound, this diastereomer as the major product. So in all these cases, the existing stereocenter, either through steric or through coordination, is controlling the stereochemistry of the newly formed stereocenter. That is here in this case, these two are in this case of epoxidation. So these are basically examples of relative stereo control. And therefore, this type of reactions are called diastereoselective reactions. Okay, now let me give you an application of that. There are numerous applications. Literally, there are hundreds of applications, probably thousands, where you start from a chiral compound and you eventually build on, keep on adding functionality until you get to the final desired target molecule. So this is, I have chosen this example because this is of relevance a little bit, because this was a drug against swine flu or H1N1, and it's called Tamiflu. This drug called as the commercial name of that, and the compound's name is called oseltamivir phosphate. And in this case, this compound was prepared from a naturally occurring chiral substrate that is called shikimic acid, and this was eventually converted to that over multi-step synthesis. This is the commercial route that prepares this one. So in all these cases, this is also called chiral pool synthesis. So in this case, the chiral starting material or the substrate you are beginning with, that has to be easily available, because if you have to prepare that, again, you are talking about how to make that one. So we'll come back to that, like how to create a chiral center starting from a chiral compound. But in this approach, you choose the substrate, chiral substrate, in a way that is commercially available easily, and that is not only commercially available, it is mostly naturally occurring. So typical examples are amino acids, sugars, and terpenes. They are easily available in large amount. So that's the advantage of having the chiral pool synthesis. The disadvantage is that first of all, you need the chiral compound as a substrate. It has to be easily available, and it has to be inexpensive, of course, for your process to be economical. But the major problem is that since you are relying on nature for this chiral compound, but almost all the compounds that are available in nature are available only as a single enantiomer. That means we are trying to prepare this oseltamivir phosphate. In case the opposite enantiomer was required, you have to have plus shikimic acid, and that is not a natural compound. So that is, you have to prepare them in the lab. So that's one of the limitations of this method. Now the second aspect is the auxiliary directed stereo control. So this is a slightly better approach in terms of the whole process, because you don't have to rely on getting the the substrate. And in most of the cases, you have to find out something that is similar in structure. Like in this case, stereochemic acid, you can see the core structure is present here. So you have to find something similar in structure. But in case of an auxiliary control, you can start from an achiral compound. For example, you have this propanoic acid, you want to put an alkyl group at the alpha position. How do you do that? So in this case, what is done, you convert your achiral propanoic acid to a chiral compound by attaching this enantiomerically pure chiral compound that is called an auxiliary, a chiral auxiliary. In this case, this is called Evans auxiliary after the name, after the discoverer of that, called David Evans. He was in Harvard. And how do you make it? You make it simply by forming a carbamate from this amino alcohol, and this amino alcohol comes from valine. So this is quite similar to the substrate control, where you are relying on the availability of naturally occurring pool of compounds that's called chiral pool. That is the amino acid in this case, which is available in a large amount, and you can convert in a couple of steps to this auxiliary. Now you control this, you have a chiral center here, a chiral compound, chiral substrate. So now you can control the incoming stereochemistry stereo center using the existing stereo center, that is the isopropyl group in this case. So what you do first, you need to analyze it. So you do that with a strong base called LDA, that is lithium diisopropyl amide, and you form something called lithium enolate. Now this lithium enolate actually can chelate between these two oxygen to form a 6-membered ring that holds it together in this place. Now, when you form an enolate, there are two possibilities. You can form this Z enolate or E enolate. These are two geometrical isomers. Now, you can see in case of an E enolate, there is a steric repulsion between this methyl and the isopropyl group. As a result, this will favor the Z enolate. That means auxiliary is already controlling the enolate geometry. This is very, very important. I'll tell you in a second. Now, what you do is that you have this enolate, you react with benzyl bromide, for example, or any other alkyl bromide, and this will approach from the side opposite to that. And the way it is happening, so this is again a diastereoselective reaction because the existing stereo center is controlling the incoming one. And this is how it happens here. So if you imagine that this enolate and this 5-member ring that is almost like a plane, and this isopropyl group will be occupying the bottom face of this plane here, what I have shown you, this dotted rectangle. Now, so therefore, the incoming electrophile has to approach from the side opposite to this isopropyl group. So this will approach from the, so isopropyl group is at the bottom, so this benzyl group will approach from the top face. So as a result, you will get this particular product. Now you can see in this case, depending on whether you get a Z enolate or the E enolate, in case of an E enolate, the methyl group will be here. So you will actually get the other diastereoisomer. So in this case, I put a term here called DR, that means diastereomeric ratio, and you are getting 99:1 mixture of these two different diastereomers. And then you can cleave the auxiliary, and that will give you the desired product, what you are looking for, and you can get, so whatever the diastereomeric ratio was, that will be reflected in this called enantiomeric ratio, what I termed as ER. And you can recover and reuse the auxiliary. So this is actually an advantageous over the substrate control one, because you can temporarily attach this chiral compound to make it as a chiral substrate, and after the reaction you can remove the chiral auxiliary. However, there are certain limitations. You need to have stoichiometric amount of this chiral auxiliary, and it involves two additional steps in this reaction. You need to attach the auxiliary, you need to remove the auxiliary. So therefore, the overall economy of the process goes down. And of course, other thing is that in case I want to have the enantiomeric compound, I need to get that it is from the corresponding D-valine, and that is not commercially available. That is not naturally available. It is commercially available, but not naturally occurring. So therefore, it is quite expensive. So fortunately, in this case, there is a different compound with an opposite stereochemistry, and so that can give you the other enantiomeric product as well. That's a different auxiliary. It is not the enantiomeric one. So in this case, that is possible, but still that's a limitation. Now that brings us to the third type. So the first two, the substrate control and the auxiliary control, they're basically diastereoselective synthesis, because your incoming stereo center or the newly formed stereo center is controlled by the existing one within the same molecule. Now, in case of a chiral reagent, you do something different. So this is an example of a chiral reagent. You are all familiar with lithium aluminum hydride. It's a reducing agent. It reduces ketone to a corresponding secondary alcohol. This is just one example. So this is basically an enantiopure variant of a lithium aluminum hydride. So you can see this is lithium aluminum hydride, and the three other hydrides you have replaced with 3 oxygen. So this is called binyl H. So this is derived from this chiral compound. This is called axially chiral compound called binyl, and so therefore it is called binyl H. Now this ketone you can actually reduce to the corresponding secondary alcohol using 3 equivalents of S-binyl H, because it's a reagent you have to use in excess, and it was formed with as a single enantiomer. Okay, now this is of course you are generating a chiral product from an achiral substrate. So in this case, the chirality present in the reagent that is controlling the stereochemistry. So in all other 2 cases, you are getting 2 different diastereoisomers. One is forming predominantly, in this case, out of 2 enantiomers itself, one is forming predominantly, or in this case, almost exclusively. So therefore, this is an example of an enantioselective reaction. Now, this is, you can imagine that this will be obvious advantageous over the previous 2 methods, but there are limitations, and this is of course the stereochemical model. So this is the binyl, this is the 2 naphthyl ring here, and this is the aluminum hydride, and lithium actually coordinates with this ketone, so you form a 6-member ring, and the hydride is delivered from only one phase, and that is dictated by the stereochemistry of this binaphthyl backbone. But there are limitations. So first of all, it requires superstoichiometric amount of the chiral reagent, 3 equivalents in this case. So, and you can imagine this is very atom inefficient process, because you are using, you can imagine the molecular weight of this compound, of this reagent, and only what you are taking from it is a hydride, that is molecular weight of atomic weight of basically 1, or if you think of in terms of molecular weight is actually 1. So it is very atom inefficient process, and of course you cannot recover the reagent will be destroyed, because once the hydride is delivered here, you will form the aluminum alkoxide, and then finally acidic workup will give you this product. So these are the limitations. So that basically brings us to chiral catalyst. But before we go to that, let's quickly take a look at it, how we are looking at this, how we are determining these enantiomeric ratios. So when it comes to the diastereomeric ratios, they are simple because they are different compounds. Their NMR will be different, so you can actually take an NMR spectroscopy and check it carefully. You can get ratio. But when it comes to enantiomer, it's a little bit complicated because their NMR spectroscopy and everything will be identical. So there are few ways of doing that. One, you can use a polarimeter, the good old polarimeter for optical activity, and then some of the other methods. Let's first talk about the polarimeter. So as I was discussing, that enantiomers will show optical activity, and then 2 different enantiomers will show opposite optical rotation, like this mandelic acid. You can see here the minus and plus, but the value will be identical. Now, if of course, if a sample is 100% of either way, it could be optically pure, and you can check the optical purity, how optically pure a compound is. For example, you have a sample of mandelic acid, and that is the mixture of R and S enantiomer. You don't know what is the ratio of R and S is mixed to it. You just measure the alpha D or the specific rotation, and you know 155.4 is the maximum one. So you can check and you can figure out by looking at it, this observed by maximum, that is 155.4 into 100, that will give you the optical purity, which is also known as enantiomeric excess. And from this enantiomeric excess, you can actually get the enantiomeric ratio. So now, effectively, what you are looking at is the enantiomeric ratio. But for that, the olden days, the method was that you prepare a compound, you measure the optical rotation. If you know the optical rotation of the enantiomerically pure compound, then you can check the optical purity or enantiomeric excess. Now, there is a limitation, of course, of this method, that and if it is a 50-50 ratio, that will be called racemic, and that's called enantiomeric ratio. Now, there's a limitation that in case you are preparing a compound which is unknown in the literature, and you do not have the optical activity or the specific rotation of the enantiomerically pure compound, you cannot use this method for measuring the optical purity or the enantiomeric ratio. So this is one of the major limitations among many other as well. So let's go with this one. You can, in that case, you can actually try NMR spectroscopy. But as I mentioned, that enantiomers will have identical NMR spectroscopy. That means if you take these two amines, enantiomeric amines, and enantiomerically pure RNA, if you make record their NMR spectroscopy, they will be identical. So what you need to do, you need to convert them to a corresponding diastereoisomers. And amines you can convert it to a corresponding amide. And in this case, an acid is used that is called Mosher's acid. So interestingly, this acid, if you look at the configuration here, it is an S configuration. If you convert it to acid chloride, it will be R configuration. Although this center is same, you should think about it, why this happens. Now, once you react this acid chloride with the amine, you get the two amide. Again, it is back to S. You can see this is identical, and these two are different. So therefore, these two are diastereoisomers. So you can measure the ratio, or you can determine the ratio by looking at either their proton NMR or the fluorine NMR. You can integrate them and you can check the ratio. Now, there are several features. So one problem or the limitation is that you need to have an additional derivatization step. That means if you have this compound, a mixture, you need to convert them to the amide. Therefore, you lost the amine. If you have to recover the amine, you have to clip the amide bond, you will lose some of it. That's the limitation. And other thing is that you have to ensure that complete reaction happened. And as you know, as I already discussed, that two enantiomerically or two chiral compounds, they behave differently in the presence of each other if they are not the same enantiomer. In other words, the rate of reaction of this R acid with S amine will be different compared to the R acid chloride with R amine. So that means they will be different in this case. So you will get two different diastereomers at a different ratio unless the reaction is complete. So therefore you have to make sure the reaction is complete. That is not an easy thing to do. And of course the product has to be analyzed without purification, because you know the diastereoisomers are different compound, their polarity can be different. So therefore if you are doing a column purification, column chromatography purification, you can actually enrich the diastereoisomers. Okay, so therefore these are the limitations. Other way of doing it is that you can, without derivatizing it, without having a separate step, you can actually use a so-called chiral shift reagent. You have some of these lanthanide compounds of a chiral ligand. This is a chiral ligand. This one actually Lewis acidic, and if it is an alcohol or amine, they can actually form this type of a adduct. And there again diastereoisomers, you can check their proton or fluorine NMR in this case. Other possibility is chiral solvating agent. So you can have this type of enantiomerically pure compound, and then they form hydrogen bond, and then again they form two different diastereoisomers. You can check with them. So these are of course better than derivatizing it, but the problem is you need to have in all these cases more than excess amount of this enantiomerically pure resolving agent or the shift reagent or the derivatizing agent. So therefore the scope is also narrow. Unless there is a functional group which you can interact with this compound, you will not be able to get the ratio. So therefore, a much more convenient method is the HPLC. It's called high performance liquid chromatography. So this is what it looks like. You have basically a solvent delivery system and a pump. These are the solvents, and it goes to a column. So this is what the columns looks like. I will tell you what is inside the column, and that goes to the detector. So the inside of this column are packed with a chiral material. So this is typically the chiral material. It's a silica gel coated with a carbohydrate derivative. So this is an example of that. And so therefore the material inside is called stationary phase, that is chiral. So therefore when the two enantiomer moves to the compound, they move at a different rate. So therefore you get different retention time. So therefore what you are looking at it, this is an example of a racemic compound that are passing through the column. You can see one is coming at 18 minutes, other one is coming at almost 20 minutes. So, and you can check their area percentage, that is almost 50-50, therefore this is racemic. Now the same compound when prepared using a chiral catalyst, and you can see this is the 18.5 minutes, it's 20 minutes, almost at the same time, and you can see one compound is coming at 99.6 and other one is less than 5%. So therefore, enantiomeric excess is 99 is to 0.2 ratio, and this is 99.6 is to 0.4 enantiomeric ratio. Other option is GC, which is very similar to the HPLC. So in this case, instead of a solvent, you are using a carrier gas as the mobile phase. And again, this column looks different. This is almost like a hair thin column, and it's a very long column. It's like 25 meters or something, the column length of it, or 50 meters some cases. And there's a column material is also a packing material is a chiral. This is the cyclodextrin immobilized on silica gel. This is one of the commercial columns. And in this case also, you will see the two enantiomers of the racemic mixture. You can see the area percentage. There are many things, that's why it is not showing 50-50. And the same compound, you can see only one of them. So therefore, in this case, the enantiomeric excess is more than 99. So that's more than 99.5 is to 0.5 ratio of the two enantiomers. Okay, so far I have introduced you three different methods. That is chiral substrate, chiral auxiliaries, and reagent. I talked about their advantages and limitations of each of these methods, and I also told you how you can actually determine the enantiomeric ratio using different tools. Now let's come to our main interest today. That is our main interest of my research group, that is chiral catalyst, which is, of course, by looking at the catalyst terms, you can imagine that this will be advantageous to all the three methods. And this will be, of course, also an example of an enantioselective synthesis. And as I was telling, in this case, it is the difference between the two, energy difference between the two diastereomeric transition states that is reflected in enantioselectivity. Okay, so therefore, the larger the difference is, the better for us. And typically, it depends from, it goes from 0.5 to 5. If 5 is the really high end, it normally doesn't happen. If it is 2 kilocalorie per mole energy difference, you can get more than 90% E. But again, this is a very simplified scenario where I'm talking about two diastereomeric transition state. As you know, there can be many diastereomers possible. So therefore, you can have large number of diastereomeric transition state that can also, or pathways that can operate. It doesn't have to be two. Now, before you go into the enantioselective catalysis, let me just tell you very briefly what is catalysis. Now, as you know that even if for an exothermic reaction, the reactants do not slide to the product like this, they proceed through an activation barrier, and this is the activation energy of this so-called uncatalyzed reaction. Now, what catalyst does, it basically lowers the activation energy of the reaction and makes the reaction faster. So in this case, the rate of the reaction is faster for the catalyzed process because the activation energy is lowered. But how does it do that? So for that, you have to look at the reaction mechanism a bit more carefully. So most of the reactions that will go through will proceed through bond formation, in some cases bond breaking as well. Now, when you form a bond, you are basically interacting two different orbitals that are overlapping to form a bond. So therefore, you are interacting a filled orbital and an empty orbital in most cases for the polar reactions. And so therefore, the HOMO of the nucleophile is interacting with the LUMO of the electrophile. And it is the gap between the HOMO and LUMO that is actually of importance. So the larger the gap is, the activation energy will be higher. So you need to lower the gap. And how do you do that? Using the catalyst. Catalyst can actually raise the energy of the HOMO so that you can HOMO-LUMO gap will be less. And this is called HOMO activation. So that means catalyst increase the nucleophilicity of the nucleophile. Other ways is that you can lower the LUMO, it's called LUMO activation. So the catalyst enhances the electrophilicity of the electrophile. There is a third possibility where both of them can happen at the same time. This is a little bit tricky. We will come to the end of the talk discussing this thing. But let's see some of the couple of examples of this HOMO enhancement or LUMO lowering. So let's consider a simple addition of a nucleophile to a carbonyl compound to form this type of adduct. So in this case, the nucleophile is adding to the field orbital is overlapping with the pi star of the carbon-oxygen bond. So therefore, you are forming a sigma bond and you are breaking a pi bond, and you can get, of course, two different enantiomers, but that's not important in this case. Now, if you think that this nucleophile is a weak nucleophile, something like alcohol or HCN and so on, which does not ionize like this. The equilibrium lies to the nucleophile side. So in that case, the neutral nucleophile or the neutral NUH bond has to attack here, which is much more difficult. So therefore, this type of reactions does not happen spontaneously. So again, in this case, the LUMO of the carbonyl interacts with the HOMO of the nucleophile. So in the presence of a base, if you take a base, it can actually pick up the proton from the nucleophile and you form a Nu minus. It can actually help this equilibrium to go to the right direction. Now this nucleophile, which is anionic now, so therefore the HOMO energy is higher or increased, so it actually can add to the electrophile or the carbonyl much more easily, and this is the example of so-called HOMO activation. On the other hand, if you take the carbonyl and add some small amount of an acid, so the acid basically can protonate. If it is a very strong acid, it can actually protonate the carbonyl oxygen, and as a result you form a cationic species. You can have a resonance structure. You can see there is basically build-up of positive charge at this carbonyl carbon. So therefore, the nucleophile, even in the neutral form, can add much easily compared to uncatalyzed process. So this is basically an example of a LUMO activation. Okay, so there are many examples of both these kinds. I will not go into that. What I will discuss today, a few examples of so-called bifunctional catalysis. So now, as I mentioned, that the HOMO activation takes place in the presence of a base, while the LUMO activation takes place in the presence of an acid. Now, for a bifunctional catalysis to happen, both has to happen at the same time. That means you have to have an acid and the base in the reaction medium. Now you are expecting your base to pick up a proton from the nucleophile and acid to protonate the electrophile. But you have an acid and the base, so they can also react with each other. So therefore, this is a bit of a tricky situation, right? So what happens in this case is that this type of concept is actually inspired by nature. So what nature does, it combines many different things together to do a reaction. There is a class of enzyme called serine protease, or carbonic anhydrase in this case. So that basically hydrolyzes the peptide bond, amide bond in this case. And for that amide bond hydrolysis, there has to be a nucleophilic addition here. And as you can imagine that this is again an alcohol. So just now what I've discussed there. And instead of a complete protonation, these two NH protons, they're actually forming a hydrogen bond. So this is not exactly a protonation, but very similar to that. So therefore, there will be a buildup of positive charge. So the alcohol can attack here. Now the alcohol will be able to attack much easily if it is ionized. So now you can see there is a base here, that is the imidazole from histidine, that can pick up the proton to ionize it or to generate a negative charge on this oxygen. So it can add here. So therefore, this is required, and this can do even better if this proton is removed, if this is ionized itself, and this aspartate side chain will be able to remove that. So there is a series of events that is happening in this case, and this part where once you add the alkoxide, you form an O minus, and that will be stabilized by hydrogen bonding. So this is called oxyanion hole. So this is what happens in nature. And so what chemist version is something very simple. So what chemist, because we cannot create the nature's active site or the enzyme active site, it's a very huge molecular weight. So what you can do, you can actually put these two different functional groups, which one can interact with the nucleophile, other can interact with an electrophile through a chiral spacer in a way that they don't interact with each other that easily, or you choose the functional group in a way that even though they interact, it is negligible, the interaction energy. So this is basically a bio-inspired concept. So our group, we worked a lot on the hydrogen bond donor, that is urea or thiourea of this type. And now they are actually very stable compound of negligible acidity, but they're very good hydrogen bond donor. And they can actually form hydrogen bond with a variety of compounds, even among themselves, or with the THF in this case. And in many cases, there are even X-ray structures known. And this is another type of compound. This is called squaramide. These are also hydrogen bond donor. So this is an example of an X-ray structure, and they can actually coordinate with many anionic gates as well. So our concept of bifunctional catalysis is that you have this type of hydrogen bond donor, and other functional group, which is typically a basic functional group. And of course, the key interaction will be hydrogen bonding in all these cases. Now, hydrogen bonding, if you think of it, it's very weak interaction. Although the energy range is huge, it can go from 0.5 to 40 kilocalorie per mole, but typically again, the hydrogen bonding energies are normally in a very narrow range. And this is very, very weak compared to a carbon-carbon bond or a metal-ligand interaction. And of course, as you have already seen, that this energy gap is normally very small range. So therefore, this hydrogen bonding can actually play a major role. And it does so in nature, although it is much weaker compared to the Lewis acid catalysis. But in nature, so this is one of the reaction. This is a Claisen rearrangement reaction, which is very difficult to catalyze. And this happens in nature using an enzyme called chorismet mutase, and with a substrate which is not really a substrate, it's like a substrate surrogate. Active site of the enzyme has been found out through the X-ray structure. You can see there are large number of hydrogen bonding that are present, and even though each of these hydrogen bondings are fairly weak, but together they actually do this very difficult transformation, which is a very high activation energy barrier. So it's almost like the Gulliver in Lilliput Island, right? So therefore, each of these so-called bonds are very weak, but a large number of bonds can bring down Gulliver. So this is what we are planning to do almost 10 years ago. We were trying to make this type of molecule called gamma-butyrolactone, because there are many natural products that contain this motif, and some of them contains a quaternary center, that is the tetrasubstitution at this point. You can see some of the example here. Now, how do you make them in an enantiomeric pure form, or in general? There are three different ways. One, you use the silyloxyfuran. This is almost like an enol. So you have already seen an example of alpha functionalization of a ketone using an enol or lithium enolate. So this is a silyl enol ether or dienol silane, this one, and this can react with an electrophile either at the alpha or at the gamma position, and mostly it happens to the gamma position. There is also a possibility of using a conjugated butanolide where you have the gamma proton that can enolize in the presence of a base to form a dienolate, and that can react with an electrophile. Other possibility is that you use this something called deconjugated butanolide. So here you remove the alpha proton, like here the acidic alpha proton can be removed, and you form the corresponding dienol. And now this dienol can react with an electrophile, and that's where your bifunctional catalyst comes into the picture. So in this case, as I discussed previously, the hydrogen bond donor will interact with the electrophile to lower its LUMO energy, and this base here, which is Bronsted base, or Lewis base, in this case a Bronsted base, it will help in analyzing this deconjugated butanolide and raise the HOMO energy. So therefore, your energy gap between the LUMO and the HOMO will be less, so therefore the reaction will take place. And the chiral spacer, they will put these two functional group in a position where the addition of the addition to the electrophile from the dienolate will happen only from a particular phase. So we'll see a couple of examples here. But this type of bifunctional catalyst was pioneered by a Japanese scientist called Yoshiji Takemoto, and they have added a diethyl malonate to nitrol. So this is an electrophile, that's a nucleophile here, and this nitro group can actually, we have seen an example of an X-ray structure, can form hydrogen bond with urea or thiourea, and this base can help in analyzing it, and then the addition takes place. So this was what our idea. We wanted to add this dienol. So initially, when we tried this conjugated butanolide, as you can imagine, this gamma proton will be much less acidic compared to the alpha proton. So that's exactly what you observe. No reaction takes place in the presence of this bifunctional catalyst. But you can actually take a deconjugated butanolide, add a triethylamine. It can easily analyze and isomerize to this conjugated butanolide, and this is thermodynamically more stable. So now this deconjugated butanolide can actually add to the nitroolefin in the presence of the catalyst. The reaction works well, but we get the product as a racemic. So this is where I'll tell you how we can actually change the catalyst structure to get a racemic compound, or where we are getting a racemic compound, how we can improve the enantioselectivity to get very high enantiomeric ratio of the product. So now here is the enantiomeric ratio. This is what we began with. We use this catalyst and we get the product with 12:1 diastereomeric ratio, because there are two different diastereomers. that can form and 50-50 ratio. We change the catalyst to a different one. Let's not pay attention too much to the catalyst structure. Only thing is that there is a basic site and there is the hydrogen bond donor, that is the Bronsted acidic site, and this is your chiral spacer. So in this case, this was the chiral spacer. Now this improved it slightly. So as we keep changing it, there is a slight improvement. In this case, we can improve even better, and then finally we come to this catalyst, which improves even better, and you can lower the temperature, you can get a better selectivity, and finally we can get to this rather gigantic catalyst where again the functionalities are remaining the same. We are putting some steric crowding around the functionality to get the product with high enantiomer selectivity. And finally we can get here, in the presence of this catalyst, you can get almost, you can see 95:5 ratio, that is 19:1 ratio of the two enantiomers. So what we check now, we check how the whether this catalyst is applicable for other substrates. You can see this is ethyl. So previously whatever we are using a methyl, and now we validate this R group here from different aromatic to heterocyclic to aliphatic, and you can see the enantiomeric ratio is most of the cases more than 95:5. So that means 90% E, and we are getting diastereoisomer in all these cases. We can also vary this R group here from simple methyl to propyl. So previous case we had ethyl, now we have N-propyl to longer chain, branching, benzyl, and even aryl also in this case. So you can get the product with very high enantiomer selectivity. So this is what we began with. Now this concept is quite general, although the catalyst structure keeps changing. We can, instead of a nitroalkene, we can use a vinyl sulfone. Again, you can see the enantiomeric ratio up to 95:5. We can use maleimide. I'll just tell you a little bit about this in a minute, or some of the other compounds as well. So now this is something we summarized very recently. So in case of a maleimide, it's something very interesting because these are called C2V symmetric compound, and you have these two sites A and B. Both of them are actually electrophilic and identical. So now if you add and if you look at the pro-stereogenicity of A and B site, they will be quite interesting. So therefore, if you add from the top at A or bottom at B, you will get this product. Whereas if you add the bottom of A or top at B, you will get this product. So that means the diagonally opposite centers are actually identical. Okay, so the way we thought about overcoming this challenge is that if it forms hydrogen bond, only this position will be electrophilic because there will be a buildup of a positive charge. Of course, this can also coordinate, but the chiral spacer will prevent only one of them from coordination. So therefore, the nucleophilic addition can happen like in this fashion. So that's exactly what happens. It works well. Again, we get the product with very high enantiomer selectivity and good diastereomer selectivity, and we can get an X-ray structure. So this is something, another aspect I should also tell you, that how do we determine the enantiomeric ratio, or which enantiomer is the major one. We can actually, there are some ways of doing that, but the most reliable one is that you get an X-ray structure containing a heavy atom, and that will tell you what is the enantiomeric ratio. We also got the X-ray structure of the catalyst that we have used, and in this case you can see that this is the thiourea hydrogen bond, NHS here, and this is the tertiary amine, and they are a little bit away from each other. There is no hydrogen bonding present. They're quite away from each other, and one face of this thiourea is actually blocked by this bulky adamantine group. So therefore, if this is binding here, the top face of this maleimide is blocked. So the only attack can happen from the bottom face. That's what I have shown here, and this also shows that this tertiary butyl group is actually very important, and whether you have here this one is NH or an alkyl, depending on that, this catalyst structure will change. So we have shown that even if you do not have this chirality, only the tertiary butyl one, you can actually get a very similar structure here, and it gives the same sense of induction with the lower enantiomeric ratio. Now, this type of bifunctional catalyst has many other applications. I will not go into the detail. I will just tell you that you can do some of the cyclization reactions. You can do some desymmetrization reaction or alkylic alkylation. You can do a Michael followed by elimination to get this alkylation or alkylation reaction. So there are some of the applications from our lab. So let me just stop here. And these are, of course, my present group. This picture was taken sometime around March this year or February this year before the lockdown happened. And this is my current group. And the last two are still the virtual members. They are yet to join my lab. They're still at home. And these are the funding agencies. They supported our work over the years. And these are some of my former students who contributed to the research that I told you today. And finally, thank you for inviting me to this fantastic lecture series. And I'll be happy to answer any question or clear your doubts if you may have.
Hello, sir.
Hello, sir. Yes.
So we have. I think my voice is echoing.
Sorry.
Okay, we have a few questions.
Yeah.
How can an optically active compound rotate the plane of polarized light? What is the mechanism behind it?
A very fundamental question. Let me just go to the slide and see whether I can. Oh yeah, there it is. So actually, this plane polarized light. So this is something that is a bit more goes to the physics than chemistry. So what basically happens is that this plane. So as I was mentioning, that light is the electromagnetic radiation. It has the electrical vector and the magnetic vector perpendicular to each other. So this is basically one of, and then we are resolving. We go to the polarizer, and you have only one plane that we are taking. And this is, of course, this plane polarized light is a chiral. So when it's interacting with the molecule, it depending on whether it is a R enantiomer or the S enantiomer of the molecule, which enantiomer. So it actually interacts with that, and then that leads to the rotation of the plane polarized light, like something that is shown inside that. So exact nature of that I will not be able to tell you, but how exactly that happens. But because the plane polarized light is, again, it's a homochiral, and that's why it is interacting with two enantiomers differently. Okay.
Why is path length not a constant parameter in optical rotation, as the solution or molecule has nothing to do with the path length?
No, molecules, number of molecules that are present in the solution, that will change on the path length, right? Let's say we have a 1 molar solution of a compound in chloroform, and your path length, you are changing from 1 centimeter to 10 centimeter. And it is actually, so the light is passing, as it's shown here, the light is passing through the cylinder or through the cell. And now if the path length is 1 centimeter or 10 centimeter, the number of molecules the light interact with on its path will change. So therefore, the amount of rotation that happens, because with interaction with each molecule, it rotates slightly. So therefore, the larger the number of molecules it interacts with, the rotation will be even more. So therefore, the path length is important. So what is not, so when you record the specific rotation, you can see the L is the path length in this case, and C is the concentration. So therefore, when we are actually measuring specific rotation, in this case, both the concentration and the path length are actually taken into the equation. So therefore, this value of specific rotation will be independent of the path length or the concentration. Okay.
If the molecules are randomly oriented in the chiral sample, why should it show rotation in a specific direction?
Okay, so yeah, this is a good question. So what happens is that, okay, they're oriented randomly, but if you just think of a single molecule in isolation in a gas phase, for example, and if you think of their relative orientation of each of them, they will be identical to no matter which way each molecule is rotated. So you're basically looking at so a tetrahedral compound, like let's say you have an H, is a methyl, bromine, and chlorine. So the relative distance from each of them, that is same in a particular molecule. So no matter which way it is rotated or oriented, that is not important. So what important is their relative position in space, and that's what is interacting with the plane polarized light. So that's why it is important.
Does the number of chiral centers in a molecule increase the reactivity? How does the chiral center affects the physical or chemical properties of a molecule?
That's a good question. So if the again, like let's say if you have one chiral center in a molecule, you are basically talking about two possible isomers, stereoisomers, that is basically enantiomers. And now if you have an achiral reagent that is reacting with both the enantiomers, the reactivity will be the same, or the reactivity will be the same. But if you have a chiral reagent interacting with a chiral compound, the transition state will be isomerism, so therefore there it will be different. Now if you just keep the reagents aside, if you think of a molecule which has large number of chiral centers, depending on where you are doing the reaction, so having the large number of chiral centers can actually lead to the molecule will not be a linear. So even if it is an acyclic compound, the molecule will no longer be linear. It will maybe oriented to give you a three-dimensional structure. And there, if the reaction center is buried inside, let's say if it is forming a helix or some sort of a tertiary structure it is forming, and if it is buried inside somewhere, then the reactivity will be less. So it is not easy to correlate the reactivity with the number of chiral center that is present in the molecule.
Why don't we consider physical parameters such as density or temperature or solvent while determining specific rotation? I feel that all these parameters would affect the populations and interconversion rates of the molecules being studied.
You're talking about the optical rotation, right? So density is important. So whatever basically I'm talking about the concentration, that is the concentration of the solution. Now, if you think about a liquid sample, then the density of the liquid is equivalent to the concentration of the solution. So in that case, the density will tell you how many molecules are there in a given amount of solution, because in that case, you'll be using, let's say, 1 milliliter of a solution. So depending on what is the density of the liquid is, the number of molecules will change. So therefore, that will affect in this case, the density will affect the optical rotation.
Why does the use of a bulky catalyst increase the enantiomeric ratio?
Okay, so it does. First of all, it does not always increase. And if I take that example, what I have just shown you guys, let's say in this case. Okay, so in this particular case, the bulky catalyst increases because what we have tried also, I did not show you all those results. Instead of this adamantyl group, we have tried some of the smaller groups also. Let's say simple phenyl or let's say ethyl also we have tried. In those cases, you can imagine that. So what we are relying on here is that this bulky group has to block one of the faces of the thiourea. The reason is that once this carbonyl forms this dual hydrogen bonding, and this is a planar compound, so therefore, so let's say this is how it oriented, it is bonded to the hydrogen bond dominance. Now the nucleophile can approach from the bottom face or from the top face. Now to block the top face, this group has to be really hindered, bulky. That is the adamantyl group is doing that. So you can see in the extra structure, this top face is completely hindered. So the bottom face will be open. Now, if this is not enough hindered, if there is a partial opening on that, then some of the nucleophile can actually add from the top face as well, because you have to understand that there is a rotation across this CN bond. So therefore, this group here, it can actually go. So in this structure, it looks like it is on the top, but in the solution, it can actually rotate, and this can actually go to the bottom also. That's what it is. The reaction is happening in this case. So in this particular case, the bulky group is important, but in many cases, it is not the steric bulk always. It is also the electronic factors that also are important. So in those cases, it can be a pi stacking, can be a hydrogen bonding interaction, and so on. So that can actually influence the reactivity.
To what extent is group theory needed in the theoretical understanding of asymmetric synthesis?
I think some of the, it may not be required group theory in this in case of theoretical understanding. It may not be required at all actually. I mean, it would be good to have an idea of the symmetry elements, but the details idea about the good theory may not be required.
Why organocatalysts are not as good as natural catalysts, where organic chemists are lacking? Where are organic chemists lacking to achieve this?
Okay, yeah, this is a good question. So you can imagine that I have shown you one example of a natural catalyst, that is the serine protease. So most of the cases when there is a natural catalyst, what happens is that you have this huge structure of the enzymes. If you know that some of the protein structure can be, let's say 100,000 molecular weight or few hundred thousand, and the active site is buried deep within the protein structure. So therefore, even though, in many cases, even though you'll see that in our body system or in nature, the main solvent is basically water, but there can be a lot of reactions happening at the pocket which is completely devoid of water. So it is very difficult to create, and first of all, create that sort of an active site or enzyme pocket where, and one thing we also need to understand is that enzymes or the active site of the enzymes, they have evolved over billions of years, and they have evolved to do a particular function. So nature, I showed you in case there are that this catalyst is applicable for a large number of compounds. Like I have seen a couple of examples where when we develop a catalyst, we take one set of starting materials, but eventually after you optimize that condition, we actually go to check their generality for a large number of compounds. So in enzymes, majority of them, they are not that general. They are very, very specific to a particular substrate, and that's how it was designed for. Nature do not care about the generality because it has to produce that particular compound again and again and again and again. And over the years, depending on the requirement, it has been modified to come to that scenario. Whereas in case of the lab or the man-made catalyst or the chemist's catalyst that we prepare, first of all, we do not want to be our catalyst to have a molecular weight of 200,000, or we want it to be very small, like these compounds are less than 500 molecular weight, because the larger the molecular weight is that, and you need a large amount of catalyst. And so we wanted to keep it simple. And so there is this famous quote by a Japanese scientist that organic chemists often get inspired by nature, like I've shown you in the case of bifunctional catalyst. But it doesn't mean that we cannot do better than nature. In many cases, we do better than nature, and at least in terms of generality, it is much better than nature.
I think we'll take one more question. Could you please discuss the origin of homochirality of life?
If I can explain that, I will get Nobel Prize. So so there are many theories. Okay, so this is a, people have been trying to come up with various explanations over the last probably 100 years or 50-60 years at least. People are trying to come up with. So there are many theories. So one theory was that so what is called primordial broth, that is when the universe was created, and then when the earth was created, there was some, I mean, the liquid, so it was mostly water, and in the water, whatever was present, that had both the enantiomers. And then some asteroid came and fell on the earth, and that had some amount of what do you call homochiral compound, and that actually influenced the precipitation or crystallization of one of them. So that's one theory. There are many different theories. So it's basically most of them goes around that you have two different enantiomers, and if they are exactly 1:1, it is very difficult to crystallize or separate them. But if it is, let's say, instead of 50-50, if it is 40-60, then you can, by some means, you'll be able to crystallize one of them, and then so one can actually go out of the solution and other can remain in the solution. So there are many theories of that. So it has people are still trying to figure out an answer of that, and hopefully in some day we will know what is the reason of homochirality in nature.
I think thank you, sir, for answering all the questions. I shall move forward and deliver the vote of thanks.
All right, sure.
First of all, we would like to thank Professor Santanu Mukherjee for accepting our invitation and taking the time out of his day to give this fascinating talk about asymmetric catalysis and its application. I think I found the bifunctional catalysis particularly interesting. We would like to also thank the Dean of the Undergraduate Program of IISc, Professor P.S. Anil Kumar, for making this talk possible. We would like to thank Team Pravega for supporting us and helping us in the organization of this talk. And lastly, we would like to thank all of you for attending this talk and hope you enjoyed it. If you did, Pravega is hosting a bunch of other talks for you, which you can check out at pravega.org. The next one of these is at 7 p.m. today, a Pravega Paradigms panel discussion in which some of the greatest names in the coaching sector talk about how they are dealing with the current pandemic. As for the elementary lecture series, we will be back on 17th of October, that is this coming Saturday at 5 p.m. IST, where Professor Malcolm Levitt will be telling us about nuclear magnetic resonance, the epitome of quantum dynamics. Till then, goodbye and take care.